So last time we saw the statement of this theorem, Artin's theorem, which is something about whether some conjugates of some subgroups of G, the union is equal to G or not, or is related to the induced map on the representation ring. Yeah. So the statement is, let X be a collection of subgroups of G, then the following are equivalent. G is the union of conjugates of all elements of X. And second is the map this from dx sum of RH, where RH is the representation ring of H. So you think of it as virtual characters of H, ring of virtual characters of H. Yeah, either way, they are the same thing. Yeah, they are isomorphic to the ring of virtual characters of G, and you take the direct sum of these things. Then this has finite cokernels. Yeah, so these two statements are equal. So this is the statement of Artin's theorem. So 2 and this another way to state 2 is that you take any guy in RG, then some power of so cokernel means if you take some sum it maybe some number of times, d number of times, then it lies in the image. Yeah, that's what finite cokernel means. Yeah, so that's another way of thinking of it. So that means so another way to think of it is if you tensor it with Q. Both are Z module. They are abelian groups. Yeah. So if you tensor it with Q, finite cokernel means that this phi induces an isomorphism. Yeah. Q or any field, so C or anything, then it induces. So if you tensor it with C, remember, if you tensor RG with C, what do you get? What is RG tensor C? So if you think of RG as virtual characters, if I tensor it with C, what will I get? You guys still with me?
Yes, sir.
Yeah. So what will you get?
So, like there was a vector space over there, right?
Yeah, it will be a vector space generated by all the characters, irreducible characters. So what is that vector space?
Class functions.
Class functions. Yeah. So you'll get all class functions on G. Yeah. So even if you tensor it with C, you will get an isomorphism between. Meaning. Not an isomorph. Yeah. So I'm not sure if this is. This is not an isomorphism, but you'll get a surjection. Phi will induce it doesn't say anything about the kernel of phi. Yeah. So it may have kernel, but I mean, of course, if you take H to be two copies of G, yeah, then of course there is no hope of this being an isomorphism. Yeah. If you consider X to be G comma G, for instance, yeah, or G comma H or something, some non-trivial. So not an isomorphism, but it will be surjective. Yeah, because finite cokernel means that the image is sort of a lattice in there. Yeah. So the vector space generated by virtual characters is same as so another way to state two is that phi when tensored with a field containing Z, field containing Q, then this phi is surjective. Okay. So we'll so I'll write. So the proof, as I said, is not difficult, but is straightforward. So we need this formula for the induced representation. Yeah. So I'll just written it down. So if V is induced representation of W to G, then in the character of V at any point G is given by, you take the average over all the elements of G such that it conjugates into H. Yeah. Okay. So maybe we'll do first one. One implies two. So one implies two. So yeah. Yeah, so let S be the union of conjugates case of all elements of X. Yeah. So let S be so S is some subset of G. We want to show that S is equal to G. Yeah. So now if we consider this, so this is the induced map, yeah, RH to this, yeah. So if we consider this in the GH and yeah, so so some irreducible character of H, so chi V, yeah. So if we consider this, then this is going to so the yeah, so yeah, so what does this say that so if Phi is a map with finite co-kernel, that means all the characters of G are captured by so up to yeah, so so 2 implies sorry, so I want to say 1 implies 2, yeah. So okay. S is in G. Yeah, so if I take an element, yeah, so let G be in G minus S. Yeah, so if S is not equal to G, then we'll have an element G in little g in G minus S. Then what is going to be the character of any representation of H? Yeah, so if I take chi in GHV evaluated at G for so for H in X and V an irreducible representation of H. What is this going to be? So you look at the formula. So what do we have to do? We'll have to look at all elements. If I want to calculate this, I'll have to consider all elements of Y such that it conjugates G into H. Yeah. But I've taken G outside all the conjugates of H, all the conjugates of elements of H. Yeah. So G in particular is not going, so no matter what we conjugate with, so G does not belong to any conjugate of H. Yeah. So this sum is empty. Yeah. So this is 0 by the formula for induced representation. Formula for character of induced representation. As G does not belong to any conjugate of H. So we can't conjugate G by any element of capital G to H. Yeah, if G does not belong to any conjugate of H, then we can't really find a Y such that Y inverse GY belongs to H, right? So that tells you that this sum is empty, and hence this is 0. Yeah. So that tells us that what does that tell us? That tells us that this all these characters chi RH. So if I take any character of representation of H, they will all vanish on G, on G minus S. So they all vanish outside S. Yeah. Now phi tensor C is surjective. Yeah, so now I have to show that this is surjective. Yeah. So now, so yeah, so the hypothesis tells us that no. So what am I trying to prove? Sorry. So I want to prove. So I'm assuming. Yeah, maybe I started trying to prove 2 implies 1 implies 2. So I want to prove 2. Yeah. So suppose. Yeah. So let's just consider S to be the union of conjugates of G. So we by hypothesis S is equal to G. Yeah. Yeah. So S is equal to G, and if I consider this guy, so what do I? Yeah. So I want to say that the co-kernel is finite. Yeah. Which is same as saying that after tensoring with C, I get surjectivity. Yeah. So yeah. So suppose chi is some yeah. So yeah. So maybe yeah. So this is not right. So I want to say that. So yeah. Maybe I'll pass to the tensoring with C. Yeah. So note that 2 is equivalent to phi tensor C from the dx sum of RH tensor C H in chi to RG tensor C is surjective. Yeah, so I have to use reciprocity. Yeah, so this is surjective. Yeah, so these are class functions on H, and you take the direct sum of all class functions on H, and this is the induced map. So direct sum of these induced map, and this is surjective. So by adjointness of this restriction and induced, it is the statement star is equivalent to, so you just do the dual, yeah? So is equivalent to saying that the map RG tensor C to direct sum of RH, which is the restriction map. So in the induced map is surjective, is same as saying the adjoint map, which is the direct sum of restriction, DH. This tensor C, H in chi is injective. Yeah. Okay. So it's so to prove 2, it is equal. It is enough to say that this map is injective, and this, of course, now we can check. Yeah. So now this is the restriction map. Yeah. So now if let's call this phi dual. Yeah. So phi dual. So of some class function on G, let's see, say f is 0, implies f restricted to H for all H in X is identically 0. Yeah. So so this is the restriction map. So to say that, so we want to say that this has trivial kernel. So suppose so f is class function on G. Class function on G. And suppose this is the 0 element of this thing, that that is same as saying that f restricted to H is all a 0 function. Yeah, but if f restricted to H is 0, then of course it is 0 on all the conjugates of H, because f is a class function. Yeah, this implies f restricted to all f restricted to all the conjugates of H is 0. Yeah, for all H in X. But this the union of such by one, the union of all these, of all this is G. Yeah. Hence, f is identical, is identity 0 class function on G I is injector. Yeah, is this okay, everyone? So this proves injectivity of this, and by adjointness, this is same as the surjectivity of this guy. Okay. So that proves 1 implies 2, and for 2 implies 1. Any questions or comments? Okay, so for 2 implies 1, so what do we have to do? So so the argument I was trying to give was actually initially was 2 implies 1. So we assume that this is this has finite co-kernel, and we want to say that G is this S. So now let S be the union of conjugates of elements of X, then S is some subset of G. We want to show that it is a whole of G using 2. Yeah. So note that for G not in S, the induced representation for any representation of a, so for G not in S and H in X, int GH or rather its character. Yeah, so I should write this chi of int GH VG is 0 for all V and H representation. Yeah, because the point is you can't conjugate G into H, yeah, if G does not belong to S. So so this tells us that every so this tells us that every cat so so this tells us that every character you get does not vanish on G. Yeah. So this tells us that image of phi, if if F belongs to, so you think of it as if F belongs to image of phi, then this is what image of phi does. Yeah, you just take the int representation. Then F is identically 0 on G minus S. Yeah. But we are saying that the image of V, image of phi is basically up to, I mean, is of finite co-kernel. Yeah. So so it can't be 0 on a conjugacy class on any element of G, right? Because this generates the whole conjugacy, whole class function. So it can't be 0 on a particular conjugacy class if it, because then it won't be generating the whole class function. Yeah. But 2 implies um, 2 implies that image phi generates all class functions on G, yeah, as a vector, as a subspace, as a vector space, yeah. So hence G in G minus S can't be empty, hence S equals G, yeah. And so S equals G. Okay, so this proves 2 implies 1. Okay, so that completes the proof of. Share gives another proof of it, but we'll not worry about it. So that completes the proof of this thing. Okay. Any questions or comments? We have about 20 minutes to discuss any concern if you have about this thing. Yeah, so as I said, the proof is not that difficult. So if you have anything, please ask.